Before I get started, I thought I would introduce some of the people who are in the gravitational waves group here at the CCA. The top row is our group. The bottom row is frequent collaborators and former members. So I'm just going to go left to right. Chiara Mingarelli is an associate research scientist here in our group. She's also on the faculty at the University of Connecticut. Her particular research interests are in low frequency gravitational waves of the sort that would be produced from pairs of supermassive black holes. David mentioned the Nobel Prize that was awarded for the demonstration that there is a supermassive black hole at the center of our own galaxy. When galaxies merge, their black holes merge, and they make the sorts of gravitational waves that Chiara studies, and she uses pulsars, rapidly spinning neutron stars scattered throughout our own galaxy, as her gravitational wave detector. So she uses these astronomical objects to detect other astronomical objects. Katie Brevik is a new addition to our group. She joined just this fall. Katie's a postdoc, so she's full-time at Flatiron. And her expertise is in modeling the progenitors of neutron stars and black holes that are found in binary systems of the kind that I'm about to talk about. And in particular, she is the primary author of a very fast computer code that can produce an entire galaxy or mini galaxies worth of binary black holes, binary neutron stars, and other exotic compact objects quickly, which is essential if you want to study the evolution of these systems and how they might imprint on galactic populations. Tom Callister is a postdoctoral fellow here as well. He studies LIGO data analysis, very similar to the sorts of things I'm going to be talking about in this talk, and also has done a bunch of exciting work on joint radio telescope and gravitational wave telescope observations of merging systems. Masha Okonkova is also a postdoc here. Masha's expertise is in numerical relativity and the numerical, the computational simulation of gravitational systems in theories beyond general relativity, so extensions or modifications to general relativity. And she's produced some of the first simulations of merging black holes in modified gravity theories. Gianni Yi is a graduate student with me at Stony Brook, and she works on using gravitational waves as probes of cosmology and the way the universe has been expanding and moving over cosmic history. And I'm going to talk a little bit about some joint work with her later in the talk. The bottom row are frequent collaborators. So Max Isi is a Hubble Fellow at MIT and an affiliate of the group, and will actually be joining us here at Flatiron next year as a postdoc. Katerina Hatsiono was a postdoc here for several years and recently departed to Caltech for a faculty position. She studies binary neutron star mergers and the equation of state of very dense nuclear density and beyond matter in these systems. Maya Fischbach is a recent PhD who is now a Hubble Fellow at Northwestern University and studies populations of compact objects like binary black holes and neutron stars. And Daniel Holtz is on the faculty at the University of Chicago. They were both key collaborators in a work that I'm going to try to tell you about later, assuming that we have time. So these folks you won't see so much in the halls, Max next year. These folks you will see around the halls if you're ever into the office, and hopefully we will all see them regularly in post-COVID times. Feel free to say hi and ask them about their work. It's a very exciting topic and a very broad topic, and they'd be happy to tell you about it. A lot of the work I'm going to be describing today has been done in the context of the LIGO scientific collaboration. I am a member of LIGO, and several of the folks in my group are as well. It's an international collaboration that runs a number of gravitational wave observatories and partners with other collaborations around the world who run other gravitational wave observatories. There are over 1,000 members, undergraduates, graduate students, postdocs, faculty members, research scientists, engineers, computer programmers, etc. And they're distributed in many institutions around the world. Here you can see, this is us. That's our group here. We are just one of many. And it really does take a village to build gravitational wave detectors and to detect gravitational waves. So I don't want you to get the idea that our group is alone in this, though of course, we like to think we've made some contributions here and there. For those of you who follow along at home or down those slides, later on I'll be talking specifically about 2 papers that have come out of our group. This is one, and this link is active. This is another, and this link is active. So if you're following along at home, you can grab them. Before I talk about the work that's specific to our group, I'd like to orient everybody about LIGO, which is an acronym for the Laser Interferometer Gravitational Wave Observatory, and the gravitational waves that LIGO detects and the instruments that we use to detect them. So pictorially, this is a gravitational wave captured here on your screen. Since Einstein, what we understand about gravity now is that it is inherent, it is an effect, a distortion of space and time. It's distinct from the other forces in the universe in that it's related to the geometry of space. And a gravitational wave is just a periodic distortion of space and time. And as an oscillating wave passes through your monitor, if you had an object that could measure lengths of a horizontal and vertical arm like this, you would see those lengths distort in the pattern here. So first one arm would get long and one arm would get short, and then one arm would get short and then long and short, etc. in this periodic pattern. To generate a gravitational wave, all that you need to do is move a mass. So very much like if you want to generate a radio wave, all you have to do is shake a charge. If you want to generate a gravitational wave, you just have to shake a mass. Now, all you have to do, gravity is rather weaker than electromagnetism. So in order to generate a gravitational wave of any note, you need to have a mass that is moving very close to the speed of light and accelerating in a very deep gravitational potential. So waving your hand in principle generates gravitational waves, but not of a magnitude that are detectable. Effectively, what's required is to put compact objects, black holes are the best, but neutron stars also work, in orbit around each other. And that periodic space-time distortion will generate a propagating wave. LIGO, the instrument, is a very precise metrology experiment. So this is a picture of one of the 2 LIGO instruments. This one is located on the Hanford Reservation, the nuclear reservation in Washington. And these arms here are about 4 kilometers long. This building here at the center is about the size of Penn Station. So it's not a small building at all. The idea is that there's a laser beam generated in this building. It goes through some optics that enhance its properties for the purpose of metrology, and then it's split and sent half down one arm and half down the other arm. When a gravitational wave comes through, it shortens one arm and lengthens the other, and the number of cycles of the laser that fit in the 2 arms changes. And so when the light runs down the arm, bounces off a mirror here at the end station and comes back, it constructively or destructively interferes, and you read out that modulated interference signal with a photomultiplier tube. The details of that are exceptionally complex, but schematically, it looks exactly like this. Laser in, beam splitter, send the laser down the 2 arms, gravitational wave changes the length of the arms, read out the signal at a phototube. The precision involved here is truly phenomenal. So the plot that you're seeing here is as a function of frequency. So this is 100 hertz, that's right in the audio band. 60 hertz, this big line right here, is a low frequency hum. You hear that in almost any electronic device if you listen closely, because it's the power grid frequency. So at audio frequencies, you're seeing here, you're seeing here the noise level in LIGO. So you just let the instrument sit there and you record the light that comes out and you measure the fractional distortion of each arm. So the arms are 4 kilometers long, and they are typically fractionally distorted by 1 part in, let's say, 10 to the minus 22. That means that the actual distortion, the length changes to which LIGO is sensitive, are something like 4 times 10 to the minus 19 kilometers, or 4 times 10 to the minus 16 meters. I calculated that wrong, sorry. Yeah, that's right. So yeah, 4 times 10 to the minus 16 meters. So a tiny fraction of an atomic nucleus. An atomic nucleus is 10 to the minus 15 meters across. So we're measuring the length of these arms to a fraction of an atomic nucleus at frequencies of about 100 hertz. The 2 LIGO detectors, one's in Washington and one's in Louisiana, they're separated by about 10 milliseconds of light travel time. And we exploit that to detect gravitational waves because we know that if a gravitational wave comes through, it propagates at the speed of light. So it has to ring each detector within, 10 milliseconds each other. The fact that LIGO is most sensitive at 100 hertz frequencies sets the mass scale of the objects that we can see. If you calculate the orbital frequency of a 10 solar mass binary, at the last orbit around a black hole, the innermost stable circular orbit right before the objects plunge, that frequency is about 200 hertz for a 10 solar mass black hole and scales inversely with the mass. So the sorts of objects that we're looking for have these characteristic masses. We don't see things that are millions of solar masses. We don't see things that are 1/1,000,000th of a solar mass or 1 Earth mass. We see things that are of order solar masses or tens of solar masses. If you look at the amplitude here, the amplitude of gravitational waves falls off inversely with distance. That's just a statement about energy conservation. If you have any wave that propagates in a vacuum, its energy is proportional to the square of its amplitude. And so the energy through successively larger spheres of radius r, or surface area 4 pi r squared, has to be conserved. So the energy flux has to fall off like 1 over r squared. The amplitude has to fall off like 1 over r. When 2 black holes are merging, I'd imagine the space-time is about as dynamical as you can get. So the distortions in lengths are order 1. If you're 6 feet in a vacuum, you go down near a black hole merger, you might be stretched to something like 12 feet. And so the amplitude of these things is something that's order 1 times, this is a dimensionless number. So we need something of units of length. It's just the Schwarzschild radius of the black holes divided by the distance to the source. And if you now write that in more reasonable units, that's something like a strain of 10 to the minus 1 part in 10 to the 23, 10 to the minus 23, times the source mass over 10 solar masses times the distance over 1 gigaparsec. 1 gigaparsec is about 10% of the way back to the Big Bang or so. So we're looking for 10 solar mass objects at cosmological distances to generate the sort of strain level that you see in the interferometer. And in fact, in a minute, we'll talk about the detected population of black holes in LIGO, and they will have sort of tens of solar masses and live at gigaparsec distances. Maybe this is a good place to pause and see, David, if there's any questions that have come up that might be of interest.
One question someone asked about the phase shift and asked whether that is less than or greater than a wavelength. What level phase shifts are we talking about here?
It's considerably less than a wavelength. We're talking about, about 1,000 nanometers in wavelength. And, this is 10 to the minus 18, 10 to the minus 16 meters. So it's millions, billions of a wavelength. And that's why the system is complicated. I haven't talked about it because I'm not a hardware person, but there's a whole bunch of tricks to build up the necessary sensitivity to see these tiny, tiny shifts interferometrically. Okay.
Another question was about Ober's paradox and the fact that this falls off as 1 over r and whether this violates Ober's paradox.
It doesn't. So Ober's paradox is really another way of stating energy conservation. If you have an infinite universe full of sources, your line of sight lands on a source at every single line of sight, so the sky is infinitely bright. But the universe is not infinite. The universe dies after, 13 billion years, which is not quite 13 billion light years because cosmology doesn't work that way, but something that order of magnitude. And so the fact that the universe is finite means we don't really have to worry about that. If you had an infinite universe and it was a Euclidean universe, you would have an Olber's paradox of gravitational waves, all the binary black holes that ever merged ever, contributing to your signal, and you would feel a steady earthquake rumbling, and you wouldn't be able to build buildings or form life or anything. You could say the same thing about photons. Really, the difference between gravitational waves and photons is not very large. If you have a radio telescope, and you have a source that emits coherently, like a maser, say, source, then you can also measure amplitudes, and the intensity falls off like 1 over r. So the same principles apply to photons and to gravitons.
And we have a few other questions about the hardware and the like, but I think we'll defer them to later and let you go on.
Okay, excellent, thank you. Okay, so LIGO has been running, a project like this has been funded by the National Science Foundation for almost 40 years. The technology required here is very hard. And so that project, I don't want to say came to fruition, it came to a middle, and what will hopefully be a very bright future, in September of 2015, with the first ever detection of a gravitational wave. This happened to be from a pair of merging binary black holes. What's shown here is the strain data. So this is the relative stretching of the arms in Hanford, Washington, and Livingston, Louisiana. And the faint red line here is the same data over here, just shifted by the delay time of the wave arriving at the two detectors, and also flipped in sign because the detector orientations induces a sign flip in their sensitivity. Or very nearly a sign flip. It's not quite a perfect factor of -1, but it's very close. And you can see that the signal in the two detectors lands right on top of each other with the appropriate time delay. From the spacing here, maybe you can't do the math fast enough in your head, I doubt I could, but the peak frequency here is somewhere around 150 hertz. And that immediately tells you that the masses involved here are, somewhere in the neighborhood of 30 solar masses. This happens to be a merger of, roughly speaking, a 30 solar mass black hole into a 40 solar mass black hole, as it turns out, when you look in detail. And relevant to some of the things I'll be talking about later, this now second row shows in the solid colored line is a numerical relativity simulation, so a numerical solution to Einstein's equations for masses that are reasonable for this event. The dark gray band, which is a little bit hard to see because it tracks that numerical relativity simulation very well, is the range of allowed general relativistic waveforms that match this data. And the light gray band is a sort of gravity theory agnostic reconstruction of this signal. So the light gray band is the gravitational wave signal that you would infer if you didn't know anything about black holes or theories of gravity, and you just asked for a signal to appear coherently in these two detectors. And so by eye, you can see first that the numerical relativity calculation is very good because it matches the reconstructed signal. And second, that whether you assume general relativity or you don't, you get very nearly the same signal out of this data, which is a very, very rough, there are better, but it's a good visual rough test that general relativity is probably the right description of this event, and that this was a 30 solar mass black hole impinging on a 40 solar mass black hole. We've subsequently published 9 other black hole mergers like this one, and have rapid alerts for about 40 more, as I'll talk about in a moment. So this was the first of many, but it was quite a bit of excitement because it was nearly 40 years worth of work leading up to this point. Another major first for LIGO was 2 years later in 2017, the first detection of a binary neutron star merger. So this binary black hole merger happened, roughly speaking, over a 1/10 of a second, and 1, 2, 3, 4, 5, 6, 7-ish orbits. The neutron star merger happened over, you can't see it on this plot, but something like 30 seconds to a minute, and comprised thousands of orbits of the pair of neutron stars. And perhaps most excitingly, see if I can, there we go. You may now be listening to a processed audio file. You can hear the neutron stars spiraling in closer, merging. And that little ding is what a gamma ray burst sounds like. So this event was seen not only in gravitational waves, but also in the electromagnetic spectrum. About 2 seconds after the gravitational wave merger, the Fermi satellite recorded a gamma ray burst, GRB 170817A. And following that gamma ray burst, the event was also observed in the optical, in the infrared, in the radio, in the X-rays. And so at one point, something like probably 1/3 of the astronomers on the planet were somehow involved in analyzing this event in the fall of 2017. Just from the fact that there's a 2-second delay here, you can tell that the speed of gravitons and the speed of photons can't be very different. Because I already mentioned these things are coming from megaparsec, gigaparsec distances. That's, millions to billions of light years worth of travel, and they arrive within 2 seconds of each other. So the speed of gravity and the speed of light have to be comparable. There were a whole bunch of other fantastic results that came out of this event that I don't have time to talk about. But it was a real bonanza and a first on par with this first. Okay, so since 1509-14, we published 9 more binary black holes and then that one neutron star event in what we call the gravitational wave transient catalog number 1. This plot is just showing their mass. So this is a chirp mass, which is a funny combination of the masses of each object involved in the binary and their distances in gigaparsecs. And the black holes, so this is the neutron star event down here. Neutron stars are light, so they were about 1.35 solar masses. And then here are 10 black holes ranging from of order 10 solar masses all the way up to 45 solar masses, and merging at distances of 1 to a few gigaparsecs, exactly as you might expect given the sensitivity of LIGO. These are the black holes that we can detect. If you turn them into primary mass, this is the heavier component, and secondary mass, this is the lighter component of the system, they're all pretty consistent with being equal masses right along the diagonal here, though we don't measure their mass ratios terribly well, so we have a range of uncertainties that span maybe a 2-to-1 merger, or in some cases even a 4-to-1 merger. So this was published in 2019. It's as I said, what we call GWTC1. Notably, LIGO, as a National Science Foundation project, is required to release its data, and we are happy to do so. And so in our public data release associated with this catalog, a number of non-LIGO Virgo collaboration authors have also analyzed the set of data and come up with their own catalogs. The first open gravitational wave catalog and the second open gravitational catalog in these 2 papers. And then we call them the IAS catalogs because the primary authors were located at the Institute for Advanced Study, again, from our first observing run and our second observing run. And people have gone on to analyze the population of these gravitational waves. In, for example, this paper, Javier Roulette is a graduate student at Princeton. And in fact, back in pre-COVID days, you would sometimes see him roaming the halls here because he's a frequent visitor to the group. Okay, so now not thinking about any individual black hole event, but thinking instead about the population of black hole events, what can we learn? Well, you might have noticed, if you're a particular acute observer, that there are 10 blacks here, and they range up to about 45 solar masses, but not beyond. One of the principal results that come out of GWTC1 is that there seems to be upper limit to the masses of black holes that participate in these mergers. And that is a real limit. There were 60 solar mass mergers. We would be sensitive to them. In fact, I will talk about one that was recently detected in a moment. So the fact that we saw 10 mergers in this sort of 10 to 40 range and none above is quite significant. And so there seems to be a mass scale, a cutoff mass scale, if you like, where the number of mergers, this plot is showing the number of mergers as a function of mass, falls precipitously. And we think that that's connected to the physics of supernova. I don't have time to go into it, but I'd be happy to talk offline about what that physics is. And the reason I'm mentioning this is this mass scale is going to become relevant for some of the cosmological work that I'm going to talk about later. Another way to show that is just these are the sort of probability densities for what we believe about the masses of the 10 individual events. And then this black curve shows where we think the cutoff mass might be if it is a sharp cutoff. And you can see it basically tracks sort of the limits on the second most massive black hole. The most massive black hole we observed we're so uncertain about its mass, it doesn't actually contribute to pinning down this limit very much. It's the second most massive one that matters, but this black curve shows you, we think somewhere, in the sort of 40 to 50 solar mass region, there is a cutoff in the black hole distribution. Right. So these are the first 10 black holes spanning through 2017. In 2019, LIGO turned back on. So in 2017, the instrument was shut off, hardware improvements. In 2019, LIGO turned back on in its third observing run, and it was truly off the hook. This is GraceDB, is a public database of gravitational wave candidate events to interface with the electromagnetic astronomy community. We publish these candidate triggers, including a map of where we think they might be on the sky so that astronomers can point their telescopes to the right place to catch electromagnetic counterparts. And through the full 03 run, which was much of 2019, comprising almost a year of live time, that's 2019 and early 2020, we have 56 detection candidates. So we've gone from a catalog of 11 to 56. And we are working to get the public data out for this 03 run as we speak, and hopefully it will drop in the next few weeks. In fact, a number of the group members here have been super busy over the last few months. Yeah, so we have more than quadrupled the sample of gravitational wave events from this third observing run. We haven't released the full data from the run yet, but we do have a few specials. Other firsts, perhaps not as significant as the first binary black hole merger, but interesting, are GW 190412, so April of 2019, which was an asymmetric binary black hole merger. What I mean by that is it was a 3-to-1 or maybe as much as 5-to-1 mass ratio. And that's interesting because these sorts of systems might form through different channels than equal mass systems. So the fact that we've seen at least one tells us something about the stellar evolution of the progenitor systems of these objects. And also, when the mass ratio is not equal to 1, there are, that's a bit technical language, but we call them higher order modes. That is to say, different types of gravitational wave emission, different patterns on the sky that are emitted when the masses are not equal. And so for the first time we detected, this shows the signal to noise ratio in one of these higher order modes. 0 is no signal. We found it at a signal noise ratio of about 3.5. That enables different types of tests of GR, because general relativity makes predictions about the relative amplitudes and phases of these different modes. And so detecting them gives you yet another handle on testing gravity theories. We also found GW 190425. April was a good month. This is a binary neutron star system, much on the surface seems like the one that was first detected, except it's too heavy. The first one that was detected has a mass of 1.35 solar masses. So its secondary mass would be here, and its primary mass would be off the plot over on this side. This system looked more like a 1.6 on 1.6 solar mass neutron star merger. And we see individual neutron stars in our galaxy that are this heavy, but none in binaries. So it is a bit of a mystery how this system formed. Our current formation theories do a very good job of explaining 1.35 solar mass neutron stars merging. They don't do a very good job of explaining 1.6 solar mass neutron stars merging. So this is an exciting puzzle for people who study stellar evolution. Perhaps even more interesting is GW 190814. This was a merger between a 23 solar mass black hole and a 2.6 solar mass thing. And the technical response to hearing about a 2.6 solar mass thing is, what is going on? The idea here is that we think, from looking at our own galaxy, that neutron stars may be as massive as maybe 2.0 or 2.1 solar masses, maybe even 2.2, depending. But it's very hard. Neutron stars are giant atomic nuclei. It's very hard to build a neutron star that is 2.6 solar masses heavy without making fairly exotic claims about nuclear physics. Simultaneously, we haven't seen a black hole in our galaxy that is anywhere near this light. The lightest black holes are 4 or maybe even 5 solar masses. And so we really don't know what this object should be, nor how it formed, but we're pretty sure it's 2.6 solar masses. So we call this, something merged with the black hole event. So this is yet another puzzle for the formation of these systems. And finally, in the weird events from the 03 run is GW 190521, so May of 2019. This black hole was too massive. So this 2.6 solar mass object is too light. This one is too massive. It is above the cutoff mass scale that we identified in our first observing run, and above the type of black hole masses that we think can easily be made from sort of standard stellar evolution of massive stars that go through supernova explosions and form black holes. It looked like an 80 solar mass object merging with an 80 solar mass object to make a 160 solar mass black hole. In addition, and this might be a clue to its formation, we think that the spins of those black holes, so black holes spin like a top, and we can measure relatively well, in this system at least, the tilt of those tops, relative to the orbital angular momentum. So if the black holes are aligned with the orbit, they just go around like this, spins are pointing up. These black holes had their spins in the orbital plane. They were tilted almost 90 degrees with respect to the orbit, and were spinning very near the limit for a general relativistic black hole, spins potentially even as high as 0.9 on a dimensionless scale from 0 to 1, 1 being the largest spin. So this system is a puzzle in many ways. And I will just say one of the ways in which you can get something that looks like this is if you don't form black holes in isolation, but you form them in disks around supermassive black holes. And we're very excited to have some visitors to our group this year, Savick Ford and Barry McKernan, who are visiting us from CUNY and AMNH, who are experts in that formation channel and are quite interested in this event and what it might imply about the formation of these systems. Okay, I'm going to pause again and take questions if there are any that it would be appropriate to answer now.
So we have a couple of them. Some I think you can answer relatively quickly. You use the term graviton. Are we talking about quantum effects or classical here?
This is purely classical. Another way to state that is if you calculate the number of gravitons that might be involved, it is phenomenally large. So we are not talking about any quantum effects in the gravity sector.
You've mentioned that the gamma ray burst arrived 2 seconds after the gravitational wave. Is that what caused that delay?
Well, we aren't completely sure, but we think that the gamma ray burst is generated when, after the neutron stars merge, there is some kind of disk of material that forms. They collide, maybe they make a very massive, a hypermassive neutron star, maybe they collapse to a black hole, but that disk spiraling around the drain generates a jet. And the jet is generated right down close to the remnant object and has to punch through a cloud of material that's sort of left over from the merger, and it takes some time to do that. And so we think this delay is related to sort of that jet breakout time scale, though the precise dynamics of this are not really settled and still debated, partly based on the observed properties of this event and also just gamma ray bursts in general.
And let me just slightly rephrase this question. If you look at an astronaut falling into a black hole, we never see the astronaut cross the horizon. On the other hand, you're talking about seeing black holes merge. How does that work?
Right, that's an excellent question. So what you're seeing is gravitational waves that are not coming from right at the horizon. They're coming from the space-time that is perturbed rather further away from the horizon. And in fact, if you want to be very technical, there's an entire class of objects which are rather speculative, but could exist, called black hole mimickers, that use exotic states of matter, matter that violates, the technical term is a strong energy condition, but it behaves a bit like dark energy. It has some extra repulsive force, to make a physical object that has matter instead of gravity that sits with a surface just outside the black hole horizon. And as you noted, if you look from infinity, things that fall into the horizon, they take an infinite amount of time to reach there. Another way to state that is if you generate gravitational waves right at the horizon, they get redshifted into oblivion as they come out to you. And so it is very, very hard, well nigh impossible, with an experiment like this that looks at gravitons that come out, to distinguish between a true black hole and a black hole mimicker that has a physical surface that sits just barely outside the horizon. There are a handful of ways to do it, but you don't see it, for example, in these in-spiral gravitational wave signals, because all the modifications to the space-time occur deep in that well where they get redshifted away.
So
yeah, I don't.
We have a number of other questions, but let's hold off till later so we make sure you have time for your talk. Rest of your talk.
Okay, excellent. Okay, actually, I am going to skip ahead a little bit. I'm going to take this out of order because I notice I've talked for a while. We're going to, maybe we'll come back to it, but we're going to skip the cosmological applications for a minute and talk about this paper, which has to do with my title. It's called Ringing Black Holes. The paper is not called that. Sorry, my title is Ringing Black Holes. The paper is a test of the O'Hare theorem. So this is paper by Max Easy, one of our group affiliates, and then some other folks, and takes us back to 1509-14. So I want to show a movie. This is a numerical relativity simulation of the sort of merger that could have generated the 1509-14 event. And so you can see here we're just fractions of a second before the merger. Down here is the gravitational waveform that's emitted in the last tens of orbits. Here are the two black holes going around each other. You can sort of see the surface here is meant to represent the gravitational potential diverges in the black holes. And as the black holes emit radiation, they lose energy and their orbit spirals in. And in a moment, they're going to get so close to each other that their horizons will touch, or their apparent horizons will touch. And that is really the point that you might call the merger of the two black holes. And once the black holes have merged, what's left behind is a single black hole, which you can think of as a perturbed Kerr black hole. So Kerr black hole is just a spinning, isolated black hole in general relativity. And the perturbed Kerr black hole oscillates and radiates away these last few cycles of gravitational wave, they're demonstrated here, in what's called a ring down, finally settling down to its sort of stationary state of an isolated Kerr black hole. And so one way you can think about this, let's see if I can run this back just far enough. One way you can think about this is we have used two black holes as a sort of hammer to hit an isolated black hole and perturb it. And during the in-spiral phase, something else is happening, but once these horizons merge, what you see, the gravitational waves that come out, look very much like the ringing down of a black hole that's just been hit by a hammer. So black hole perturbation theory is an old subject. It goes back to the mid-20th century, late 20th century. And the normal modes, the ringing tones of a perturbed Kerr black hole have been calculated. And their gravitational wave emission has been calculated, and their emission is just damped sinusoids at certain frequencies and damping rates. So it really behaves very much like a damped harmonic oscillator. And this is a plot from a paper by Matt Giesler, who's one of my co-authors on this work, that shows in blue the gravitational waves that you would calculate for a 1509-14-like event with numerical relativity. And in orange, what you would get by adding up 7 damped sinusoids, just exponentially damped sinusoids, regular old simple harmonic oscillator modes, starting at the instant that the two horizons touch. And the difference here between the blue and the orange curve is about 1 part in 10,000. So this is a numerical experiment that demonstrates that right from the point where the horizons touch, you can treat the gravitational wave signal as if it is just a perturbed Kerr black hole ringing down. Now, people who do perturbation theory might be kind of surprised by this. I certainly was when I first saw the result, because if you actually look at what the space-time looks like, it does not look like a linearly perturbed black hole. This does not look like the kind of thing you would normally use normal modes to represent. It looks like a peanut. And the potential here has all the sorts of weird spikes and still has 2 sort of well-separated dips sitting inside the parent horizon here. So this doesn't feel like the kind of thing you'd apply perturbation theory to, but in point of fact, you can. And the reason that this is interesting is because much like early quantum theory predicted the spectrum of the hydrogen atom in terms of a single physical constant, what is the energy of the ground state of a hydrogen atom? It's 13.6 electron volts. That's the Rydberg constant. If you know quantum mechanics, once you know that energy, you know the emission and absorption frequencies, you know the energy gaps in all of the lines of the hydrogen atom. You can just sit down and calculate it on paper. In the same way, if you know the mass and the spin of a black hole, general relativity tells you the frequencies and the damping rates, the quality factors, of all of these ring down modes. And so if you can find multiple ring down modes, you can use the first ring down mode to measure the black hole's mass and the spin and predict where the entire rest of the modes ought to be. This program is called black hole spectroscopy. And then you can go and check, do you actually see the modes at the frequencies and damping rates that you expect? And so I want to focus on this right-hand plot here. This is showing the amplitude of the fundamental mode, the first overtone and the second overtone of the perturbed black hole, as inferred from the ring down that we observed in the 1509-14 GW 1509-14 event. So this is real data. 0 here is the point at which the horizon started to touch. The dots and error bars show the data with real uncertainties, and the blue curves are the fitted sums of damped sinusoids. They don't look like sums of damped sinusoids because this has been whitened by the power spectrum of the interferometer noise, which distorts different frequencies differently and gives them this kind of janky appearance. They really are damped sinusoids fit to this data. And the lines here are composed of the sum of 3 modes, the fundamental, the first overtone, and the second overtone, with varying amplitudes. And these are the constraints we obtain on the amplitude. So first we measure the amplitude of the fundamental to be something like 10 to the minus 20, a few 10 to the minus 21. But now focus your eye on this part of the plot. This is the amplitude of the first overtone against the amplitude of the second overtone. We aren't sure which of these two contributes to the signal. We don't know that, but we do know that you can't have both of them be 0. So purely the fundamental tone of the black hole is ruled out at very high confidence because it's this point, 0 amplitude in the first and second overtones. We prefer there to be, 4 10 to the minus 21 in the first overtone and nothing in the second, or maybe 4 10 to the minus 21 in the second overtone and nothing in the first. We can't really distinguish between those two, but we can definitely state that there is, the fundamental and at least one additional mode in this black hole. And that lets us perform a test of general relativity. We use the fundamental mode to measure the mass and the spin. We look for the first overtone at a frequency and a damping rate that have been perturbed from their general relativistic values by these fractional perturbations in frequency and in damping rate. So the dotted lines here are no perturbation to GR at all. The first overtone is exactly in the place where you expect to find it. And here is the sort of credible interval that we find. It's completely consistent with GR. And in fact, the width of our measurement of the perturbation to the overtone's frequency is about 20%. So you could call this a 20% test, whether you want to call that precision or not, depends on whether you're an astronomer or a physicist, a test of general relativity in the lingo is in the strong field regime. We are looking at the properties of the remnant black hole deep inside its potential well. And we are confirming that those properties are described by general relativity to plus or minus 20%. So this is done just with the first such black hole merger. By the end of the third observing run, we have about 50 black hole mergers, if you just stack them on top of each other, you take 20%, you divide it by the square root of 50, you get a few percent test of general relativity. So just repeating this test in every black hole, it doesn't actually quite get you here. This 150914 is advantageous for this sort of measurement, and other systems are not so good. So we don't quite expect to get a 3% measurement, but we expect to get a sub 10% measurement of whether GR is correct from this black hole spectroscopy program. And I think I would like to have a long question period because I see there's like 20 questions in the Q&A. And so I will stop there. And if you want to hear about the cosmology work that we do, you'll have to just stop me in the hallway sometime, and we'll sit down for a cup of coffee.